Okay, here's part 2 of the charge to mass ratio video where we get into the equation part of this stuff. So here we are at the starting point where we have the force made by the charge of the magnetic field and the velocity of the electron is equal to the force made by the charge of the electric field. And that beam of electrons is adjusted so that those forces are equal, meaning that it's projecting on to the end of that cathode ray tube to where like it's not looking like it's deflected. It's like that straight line because those forces are balanced right now. So another way to say this is the charge exerted by the strength of the magnetic field times the velocity of the electron is equal to the charge exerted by the electric field. So if you were to take a minute to solve this equation for V, the velocity of the electrons, what would that look like? I am going to give you just a second to think about it, but it's pretty simple once you actually think about it. We're just going to divide both sides by BQ, and that leaves V on this side, and then this side is going to be the charge of the electric field divided by the charge of the magnetic field, and we can actually eliminate the two Q's so that we have the velocity of the electron is equal to the electric field divided by the magnetic field. It's equal to the ratio of the electric field, strength of the electric field to the strength of the magnetic field. The velocity of the electrons is equal to the strength of the electric field divided by the strength of the magnetic field. So this equation reveals that the forces are balanced only for electrons that have a specific velocity, v. So they're going to be going a certain velocity when those forces are balanced. But then if the electric field is turned off, only the circular force of the magnetic field remains. So you remember that those magnetic fields are caused by Helmholtz coils, which create a uniform magnetic field in between them. And what's happening here is those electrons, as we saw before, they circle around magnetic fields. They make a circle around a magnetic field. So there we have it. There's the circular electron path around the magnetic field. How cool is that? Causing a centripetal or circular acceleration of the electrons. So you'll notice that this circular path is actually, it's like brighter than it was when it was just the individual path. I just think this is such a cool experiment. You can bend light. It's so cool. Using magnetism. So the electrons follow a path with radius r. There's our radius r of this circular path. So now we're going to connect this to another equation that usually in physics class you would learn this first, but we're starting with the atoms first, with the small stuff first. So this is maybe your first exposure to this. The second law of motion says that the force equals mass times acceleration. So basically, like if you have a very large object like a semi-truck and it's going very fast, it's going to create a lot of force if it hits something, right? It has a lot of force moving with it. So we can make that very small too. We're going to figure out how this equation relates to this equation. We can actually put chunks together here. So take a look at it for a second. Figure out which part is force, which part is mass, and which part is acceleration. What could it be? Think about it in chunks. And I do see that there is m for mass, so that's easy enough. So this chunk over here, the force created by the force is going to be the charge created by the strength of the electric field and the velocity of the electrons. And then the acceleration is going to be this, that velocity squared divided by the radius. Going faster and faster around that circle, right? Squared is is the indicator of acceleration there. Because it's like as fast as it's going times as fast as it's going to go, faster and faster. So the strength of the electric field times the amount of charge times the velocity of the electron is equal to the mass of an electron. So we have what we're looking for right here. We just don't know the number that it would end up being here. The mass of an electron times the velocity squared divided by the radius of the circular path of the electrons. So this chunk is acceleration. How fast is it going around that circle? Here's that circular path of those electrons around the magnetic field. So from this equation, we can solve for the charge to mass ratio. So how would we do that? When we get to that charge to mass ratio, then we'll be able to find out that infinitesimally small mass of an electron. Charge to mass. So let's take a minute to solve for the charge to mass ratio here. What do we need to do? This is kind of complex because it involves a square root. So what it ends up being is the charge to mass ratio, charge to mass, is equal to the ratio of the straight trajectory velocity. So what ends up happening here is when we do the square root, no longer are we talking about acceleration. We're just talking about straight up velocity, the straight trajectory velocity, which we can find out by looking at that straight path in the cathode ray tube. Not the circular one, but the straight one like Thomson used, divided by the magnetic field times the radius of that circular path. So in order to calculate that velocity, the straight trajectory velocity of an electron, Thomson used a measured amount of electric field, that electric field that's going straight down like this, and a measured amount of a magnetic field, B. So when it was balanced out just right, the beam of electrons would go on that undeflected path, and that's how he knew it was balanced. And that's how we would get that, like, the V equals, yeah, that's how we would get this. When we have this, we find out this velocity from this balanced electrons, electric versus magnetic field. Okay. So once it was balanced, then he removed the force of the electric field, so only the magnetic force was acting on the electrons, and measured the distance between the undeflected spot and the deflected spot. So how far is that deflection just from the magnetic field? And what that gives us is another way of looking at the radius. The undeflected spot, this is like the radius of those electrons in their circular path. Sorry about that. In their circular path around the magnetic field. So the average of many experimental trials produced the value that the charge to mass ratio is going to be 1.759 times 10 to the 11th coulombs per kilogram. So a coulomb, in case you don't know, is the charge, like 1 coulomb of charge is the amount of charge from 1 ampere flowing for 1 second. It's kind of hard to make analogies to things like, I was hoping to be like, that's like 1/10 of a refrigerator like amount of charge, but it's not exactly, there's like a lot to be learned there, and I can't get into all of that right now. But to put into perspective a little bit, what this is saying is that if you had a kilogram of electrons, the charge on them would be 1.75.9 billion coulombs of charge. So basically, that would never happen because you could never get like a kilogram of electrons stuck together. I mean, that would just be crazy. But if you could, it would be insane how much charge they had. That's just kind of what that is saying. So then he took that and he solved for mass. So in order to get mass on its own, he did the charge divided by the charge to mass ratio, which ends up being 1.602 times 10 to the negative 19th coulombs, teensy tiny amount of coulombs, divided by 1.759 times 10 to the 11th coulombs per kilogram. So this is like, if you had a kilogram of electrons, how much charge would they have? And then you're getting rid of like the amount of charge there. So it turns out the mass of an electron is 9.107 times 10 to the negative 31 kilograms. So meaning like 0.31 zeros, 30 zeros, I guess, and then 9.1. So to put that into perspective, we talked about that one proton is 1 atomic mass unit. So let's equate kilograms to atomic mass units and say that the mass of a proton is about 1.672 times 10 to the negative 27th kilograms. So the important thing that we're looking at here is this exponent here, the negative 27 kilograms. That's how big a proton is. So at this amount to the negative 31 to the negative 31st kilograms, so what we're looking at here is a difference of like 4 zeros basically. One electron is about 0.005 atomic mass units. You can see that difference of 4 place values is right there. So one electron is about 5/10,000ths of an atomic mass unit. And that is the mass of an electron. So I hope your brain doesn't hurt. I hope you're doing good. And that is the video. Thanks.